Hello and welcome to C++ Weekly. I am your host, Jason Turner. I am available for code reviews and on-site training. Now, I am doing some workshops at upcoming conferences, and I'm not exactly sure when this episode is going to air, but if you have any interest in coming to one of my workshops, be sure to check out the video description below. Now, I've had a few corporate training clients recently who are concerned about things like GPU programming, and this is something that I have literally no experience with at all. And so I decided that I needed to learn something about it, see at a high level how it works, what can I expect from this, and what are the limitations and that kind of thing. Now I know back from when I was a CPP cast host that there are a bunch of options for GPU programming things that can kind of just magically work with C++, or at least that's what I've been told. And so I decided to check it out. And if you're anything like me, you come across this graph and you say, I have literally no idea where I should go from here. So you do a little bit more research and you find yourself landing on something like this. And you're like, which compiler do I download? Do I get one from NVIDIA? Do I get one from Intel? Do I get one from CodePlay? I have no idea. What does this all mean? Well, as I was looking at this, I noticed this thing called AdaptiveCpp, which was apparently previously known as OpenCpp. Here is AdaptiveCpp. It claims to just be a community-driven, high-performance, heterogeneous programming environment for C++ that can work across multiple threads or GPUs just kind of magically. And so I thought that I would give it a go. And of particular interest, if you go to the AdaptiveCpp GitHub repository here, you find this. C++ standard parallelism. Additionally, AdaptiveCpp features experimental support for offloading C++ algorithms from the parallel STL. See here for details on which algorithms can be offloaded. AdaptiveCpp is currently the only solution capable of demonstrating C++ standard parallelism performance across NVIDIA, AMD, and Intel GPUs, and in most cases outperforms vendor compilers. Well, this sent me down quite the rabbit hole because I really wanted to test this for you, my viewer. So I don't currently have any devices with a GPU that natively run Linux, and getting these things running on Linux is easier than doing it on Windows, particularly these LLVM-based compilers and such. And plus, I thought that's more realistic to the things that my students use. They are using supercomputing clusters that are running Linux with a bunch of GPUs. So I needed to test this out myself. Now, I'm normally a Monjero guy. That is what I use for all my Linux virtual machines. But I thought it would make sense to do something more mainstream to make this easier. Now, I'm not gonna bore you with all the details here, but let's just say I installed Mint once or twice. I tried to install Monjero and couldn't get it installed, and then I installed 2 different versions of Ubuntu as I was trying to get to something that could actually support the drivers for my GPU on my laptop, which is just an AMD integrated thing, in a way that would work with something like an OpenCL backend or SYCL backend. This was a gigantic pain, but I did eventually get it working, so I was able to run all this native with nothing else running and record a bunch of data for you. Now, let's get to the actual problem here. I am going to do a game of life simulation. And I've written game of life versions several times before, so I'm familiar with it. But also, it is kind of embarrassingly parallelizable. You have the game board current state, and you need to iterate it to the next state. And to iterate it to the next state, you follow a simple set of rules. You take the current game state, and you do a transformation on it. For each cell, you count the number of neighbors, and then you apply the appropriate rule, and the result is the value of the new cell in the new game state. So I have up here my gameoflife.cpp that you can check out. I do have it so that you can print the game board to see out if you were so inclined, but for the most part, I'm running this just as a simple performance test. I set a couple of gliders, and then I iterate it for some number of iterations. And the iteration's pretty straightforward. I take the current input board and the output board, so I overwrite all the data in the output board. I do that count transformation on each cell of the input board, and then I perform a swap at the end of this, so that I'm just swapping back and forth between the same two buffers and never having to do any sort of extra allocation on each iteration. Now, I would have preferred to have made these game boards something that live on the stack, but if I want to be able to offload this to the GPU, that requires something on the heap. And AdaptiveCpp is smart enough to say that if you create this thing on the heap, it's going to make a special pointer that it knows how to automatically move over to the GPU. And that is super amazingly handy. Now, the actual, quote, magic, if you will, here, is that this is really just simply a standard transform. For each element, I want to count the neighbors, return the appropriate state, and use that output to populate the output board. It's very straightforward. Now, C++ 17 gave us parallel algorithms, and I've done a simple episode about parallel algorithms in the past. And I'm saying this is parallel and unsequenced. I don't care what order these things execute in, just execute them. Now, I took this program and I ran it a number of times. And I'm going to have playing here in the background the actual raw execution of these things, where it's running and calculating timing data for a 10 by 10 board run 5 million times, 100 by a 10 run 500,000 times, etc., up to a 10,000 by a 10,000 executed 5 times. Now, I did this intentionally to scale it so that there are exactly 500 million cell calculations that need to happen, and kind of compare apples to apples. Now, before I get to the actual graph data, I should point out the parallel algorithms versions of these use Intel's thread building blocks, and that's because that's what Clang and GCC have both chosen to use as their backends for parallel algorithms. Although, come to think of it, I should point out that I did use GCC's standard library for both Clang and GCC, and I might have had slightly different results here if I had used Clang's standard library instead. Okay, so here are the final results of this. I've got the raw timing for GCC and Clang, and I've got a graph here and we'll zoom in on it in a moment. But we can see, first of all, that if we're doing a single-threaded serial version of this, GCC, with the code that I wrote, is consistently almost exactly 2 times faster than Clang, and that should bother us. And I don't know why that is the case. I'm going to dig into that. That will be a topic for a future episode. Now, if I use the thread building block backend for the parallel algorithms, then I see that I go from, somewhere at my peak performance about 5 seconds, this is all in milliseconds, 5.2 seconds, down to 0.8 seconds to execute. So I'm looking at getting about a 600% parallelism realistically using the standard algorithms, and I didn't do anything at all except compile with parallel algorithm support. So that's kind of amazing. On my laptop, I've got 8 cores, 16 threads. I would have hoped for a little bit better performance than that. And we can see approximately the same improvement with Clang going to the parallel algorithms as well. But then we have here the number for the adaptive C++ with CPU parallelism. And I'm getting, again, about the exact same speed realistically as the Clang one. And that shows the fact that the adaptive C++ backend, it's actually using LLVM and Clang. Now, I have two different timings for when I actually move to GPU calculation. And I didn't change the code at all. All I did is recompile it so that it says use the GPU for parallel algorithms. It's the only difference that I made, except for the fact that I had to allocate these things on the heap like I mentioned before, and that was definitely a large part of the learning curve for me. And fortunately, the folks on the Adaptive C++ Discord were really helpful, and they helped me get over a couple of these humps. Okay, so we have both cold and hot. Now, when you run a program that was compiled with Adaptive C++ for the first time, it has to dynamically recompile and create a cache of your code. So you expect the cold run to be slower and the hot run to be faster. And that wasn't true 100% across the board here, but we can see that there is some definite extra cost that we need to dig into. So if we're doing parallel algorithms, and you can see the yellow and orange bits of the graph and the blue and green versions of the graph, and if you're colorblind, they're the spiky bits. It doesn't make any sense at all to do parallelism with a 10 by 10 game grid. This is costing me a huge amount of time to do this, and an even more huger amount of time in the case of offloading it to the GPU. So it's actually more expensive on the smaller grids to use the GPU. But once I get down to a 100 by 100 grid, I can start to see that the GPU is actually now starting to outperform the regular CPU parallelism here. And I can also see that the cold versus hot, the cold is slower than the hot one. And we reach this super sweet point here at 1000 by 1000 grid. Now this is 1000 by 1000, and each cell is 1 byte because it's a Boolean. So that's, well, it's 1,000,000 bytes. So it's less than a megabyte per game board. So there's 2 million bytes of game boards out there in play. And we, at our absolute peak, which will probably become the title for this episode, with no real extra work on our part, have gone from the worst case scenario of Clang, because this is using Clang's backend, to the best case scenario of AdaptiveCpp with the Clang backend offloading to the GPU, being 68 times faster. And all I had to do was pass a different flag to my standard algorithm and recompile with a new compiler. That's really cool. Now, I did set myself up here for an algorithm that I knew was embarrassingly parallelizable. And I do have to take into account that there is a bit of a curve to this graph. So I'm going to go ahead and hide the most expensive parts here so we can zoom in a little bit on the graph. And like I said, we can see that GCC is consistently about 2 times faster than Clang, and using the parallel algorithms is, again, several times faster. And if we go ahead and also remove from our graph the serial versions of things, then we can get a bit more of a zoom in as to what we see here now. So lower is better in this particular case. And if I am using parallel algorithms, then I get better and better performance the larger the problem set is that I'm working on. If I'm using the GPU, then I have this little bowl where it's clearly more expensive to use it on small problems and clearly more expensive to use it on problems that are too big, and a nice little trough here where there's a sweet spot where we can get 68 times the performance in the right cases. So anyhow, I hope this was an interesting episode for you, and I do encourage you to go check out Adaptive C++ and to check out the link. I will have a link to the program that I actually wrote here, so you can test it yourself. It's 300 lines of code. If you want to look into why Clang is so much slower than GCC, feel free. I have a hint of a reason as to why, and I will almost certainly make an episode about that coming up in the future. But otherwise, thank you for watching this episode of C++ Weekly. Be sure to subscribe, and I'll see you in the next episode.